Okay, in this example, I'm going to use this example to demonstrate binomial distribution can be approximated by what? Normal approximation. Can be approximated by normal distribution. And this is also a special case for central limit theorem, okay? And this is a given example. A fair coin is flipped 100 times. And we are interested in X. X is total number of heads resulting in 100 flips. It's X1 plus X2 plus all the way up to what? X100. For example, what's my Xk? Xk is 1 or 0. It's 1 if the case flip is a head. If it's a tail, otherwise, if it's a tail, we count as what? We count as 0, okay? Okay, Xk is 1. If the case flip is what? Is a head, we count as 1 head. Otherwise, we count as what? 0 heads, right? If you see a tail, you count as 0 what? 0 heads, because you don't see a head. Now look at here. Let's say this is the one realization. You make 100 flip. And the pattern is head, head, tail, all the way up to head. So X1, you see a head, so it counts as 1 head. X2, you see head again, it's still 1. X3, you find a tail, so you don't see a head, 0 head. And keep tracing this until X100. You still, well, you see what? A head, counts as 1 head. So in this case, total number of heads resulting is X. X is this X1 plus X2 plus all the way up to what? X100. So you add how many heads you see, okay? You add how many heads you see. So we call this a sample total, okay? Total number of heads resulting in 103, okay? Now, as you can see, Xk can only assign what? 1 or 0. So the distribution of Xk, you follow a Bernoulli distribution. And how likely you see a head is pi. Pi is probability of seeing a head. Okay? If this is a fair coin, this is 1/2. It means you have 50% chance to see a head, you have 50% chance to see a tail, 50-50. That's why we call this is a fair coin, okay? Okay, recall, we know Bernoulli random variable can only assign 2 possible value. If you see a success, in our case, success is seeing what? A head. You count as 1. If you don't see a head, you see what? It's called you see a failure. Okay? That is what? 0. If you see a tail or you see a failure, that's a 0. Why 0? No success. Okay? So Xk follow Bernoulli. Xk equal to 0, that chance is 1 minus pi. Xk equal to 1, that chance is pi. And 2 possible values. The probability should add up to what? To 1. Okay? Now let's see. If Xk follow Bernoulli, what is the mean of a Bernoulli? Is summing all possible value of Xk. Xk times probability Xk. Okay? So when you don't see a success, it's 0 times what? Xk equal to 0. Plus, you do find a success. In our case, you find a head times probability Xk equal to 1. So 0 times everything is 0. 1 times what? Probability Xk equal to 1, that's pi. So 1 times pi is pi. So mean of a Bernoulli random variable is the probability of getting success, which is pi. Okay? Now, what is the variance of Xk? Variance of Xk is the expected value of Xk minus expected value of Xk, the whole thing squared. And this is Xk minus expected value of Xk. The expected value of Xk is what? We just find is a probability of getting success. So Exk is pi. So what's the variance Sk by definition? Okay, is this. And we know Exk is pi, plug it in. So how we find this? Well, summing all possible value of Xk minus pi squared times Py Xk. Okay? Now, just like before, Xk has only two possible values. When Xk is 0, so this 0 minus pi squared. But how likely Xk equal to 0? That chance is what? 1 minus pi. Plus, another possible value for Xk is 1. So 1 minus pi squared. How likely Xk equal to 1? That chance is pi. Okay? So here, this is pi squared times what? 1 minus pi. Plus 1 minus pi squared times what? Pi. So let's figure out the common factor. Pi times 1 minus pi. The first term, you see pi left. The second term, you find 1 minus pi left. And pi cancel with minus pi. Okay? So this ends up to be pi times 1 minus pi. So the variance of a Bernoulli random variable is a product of two probabilities. One for success, the other one for failure. So it's very easy to remember, okay? If I flip the coin 100 times, how likely the number of heads resulting is between 40 and 60. Okay, this is a typical application of central limit theorem. Okay, now recall what's a central limit theorem. Given x1, x2 up to xn is a sequence of what? IID random variables. Okay? First I stands for what? Independent. And this one, identical. Okay? Given x1 up to xn is a sequence of IID random variables with common mean Ex1 equal to mu, and with common variance variance x1 equal to sigma squared. Okay, with common mean and variance. Then when n is large, how large usually we call large? Well, for this course, if we don't talk about special case, n greater 25 is big enough, okay? When n is large, then by central limit theorem, sample total. In our case, x1 plus x2 plus all the way up to what? x100, okay? Should follow approximately normal. with expected value of sample total and the variance of the sample total. With mean and variance, okay? With mean and variance. And if you read my YouTube video, you know this is what? This is N mu, this is N sigma squared. In our example, N is 100. Mu is EX1, okay? EX1. And we know EXK. XK is a Bernoulli random variable. So mean is a probability of getting success. And getting heads, our chance is 1/2. So that is what? That is 50, okay? And how about variance of sample total? N times sigma squared. We know sigma squared in our case is what? N times variance of X1. X1 is Bernoulli. So its variance is probability of success times failure. But since it's a fail coin, both equal to 1/2. So this is 25, okay? This is 25. And 25 is what? Is 5 squared, okay? 25 is 5 squared. So in this case, look at here. X1 up to Xn is a sequence of IID random variable, independent and identically distributed random variable. It's very easy for you to figure out if you use what? A box model. 1 and 0, okay? 1 and 0. Fair coin means 1, 1. And you make what? 100 draws from the box, okay? With replacement. Since this is with replacement, the draws are what? Huh? The draws are independent, and both independent and what? And identical. Okay? This is why X1 up to X100 is IID, okay? Because the draw are made what? With replacement. And this X is actually X1 plus X2 plus all the way up to X100. That's why we call this a sample total. Okay? So recall, a binomial random variable is the sum of n independent and identically distributed Bernoulli random variables. So this number here is sum of 100 independent and identically distributed what? Bernoulli random variable. So this distribution is binomial. And because central limit is 0, this can be approximated by what? By normal distribution, okay? So look at here. To find the probability that sample total, which is X1 add up to X100, is between 40 and 60, okay? Look at here, what's the chance? This is sample total, which is the sum of 100 independent and identically distributed what? Bernoulli random variable. Because n here is 100. Way bigger than what? Than 25. So, because now n is 100, way bigger than 25. So sample total by central limit 0 follow approximately normal. And the center of the normal distribution is the expected value of sample total. Okay? And we just find expected value of sample total is 50. And we want to find how likely sample total is between 40 and 60. This is 40. This is 60. So we just want to find how likely, well, we want to find the size of the shady area. And how can we find the size of the shady area? It's standard procedure, okay? We call standardization. Any variable, subtract by its mean, divided by standard deviation. We're gonna convert to z-score. And we know mean of the sample total. It's a fair coin. You flip the fair coin 100 times. You expect to see what? You expect to see 50 heads, okay? You expect to see 50 heads. So this is minus 50. Divided by standard deviation, okay? Is square root of variance total. And variance total is what? 25, 5 squared. You take square root, so this is just 5. Okay, just 5. Now, let's do the standardization here. 60 minus 50 divided by 5. This is positive 2. And here, 40 minus 50 divided by 5. This is what? Minus 2. So the probability we are looking for, sample total between 60 and 40, convert to z-score, is z between what? 2 and minus 2. By 68, 95, 99.7 rule. From 2 to what? Minus 2. Cover about 95%. If you check the table, it's actually 95.45%. Okay? This is the answer, okay? This question demonstrates the relationship between Bernoulli and binomial, okay? And the binomial is sample total. And by central limit 0, when sample size is large enough, the sampling distribution will follow approximately normal. So sample total, approximate normal, okay? From 40 to 60. And by standardization, we can use standard normal table to find the probability is about what? 95.45%, okay? When binomial distribution are approximately binomial, a common question is asked. How large n? N is a sample size. How large n is considered large enough? Okay? There is a checking condition. N times pi should greater equal to 10. N times 1 minus pi should also be greater or equal to 10. In our example, okay? In our example, a fair coin. We flip the coin 100 times. A fair coin, pi means 1/2. 100 times 1/2 is 50. 50 obviously is way bigger than 10. Okay, so this one is okay. Second condition, a lot of students in the exam I find in the past is they don't check n times 1 minus pi. They check n times pi times 1 minus pi greater equal to 10. Listen to me, this is wrong. You should check n times what? 1 minus pi. In our case, when we flip the coin 100 times, and it's a fair coin. So this is also 50. It's also way bigger than 10. Okay? That's why we can use what? Normal approximation. Okay? It's very important. When binomial distribution are approximated by normal, you need to check these two conditions. Make sure they are both greater equal to 10 to use normal approximation. Some book use what? Greater equal to 5, and this is greater equal to 5. That's fine too, but you don't get what? Good approximation. Not as good as you check both greater equal to 10. Okay?